what is our strategy for solving systems of linear equations? We use elementary row operations to bring the matrix of the system to reduced row echelon form and then extract solutions from the row echelon form. But how do we know that the reduced or simplified system of linear equations has exactly the same solutions as the original system of equations? To show this, we will prove the following theorem. Elementary row operations do not change the solution set of a system of linear equations. Now, so how are we going to prove this? When we prove theorems, it's important to understand what is given and what is our goal and destination that we need to reach. But in order to understand this, we first need to set up some notations. Now, in this case, we have two systems of equations. So let's just denote one system of equations like this, and another is a new system of linear equations that we are going to denote with a prime. And here we apply one elementary row operation. So if we show that applying one elementary row operations does not change the solution set of a system, then it will follow that applying a sequence of elementary row operations will not change the solution set either. So we're going to focus on a single elementary row operations. Now, a system of linear equations is characterized by a matrix. So here we have a coefficient matrix A, and the entries of this coefficient matrix we will write Aij. And so we have the transformed matrix that we're going to call A prime. And the entries of this matrix will be called Aij primes. And also, well, we have a coefficient matrix, but also we have the right-hand side constants. So here we will have the constants, so bi's. And after the transformation, we will call these constants bi primes. So this data specifies the original augmented matrix and the augmented matrix obtained after we apply an elementary row operation. All right, so we have three types of elementary row operations. So now let's recall them. So we have type 1. Is when we add to one row a multiple of another row. So let's say we have row S, and we say that new row S is row S plus a constant times row P, right? So then we have type 2 elementary row operation is when we take a row and multiply it by a non-zero constant. So we say row S prime is K times row S, where K is not equal to 0. And finally, we have type 3. is when we take two rows and interchange them. So we'll write it like this. So what we need to show is that for elementary row operations of these three types, the statement of this theorem holds. So this means that if we take any system of linear equations with an arbitrary augmented matrix and apply one of these three types of elementary row operations, then the resulting matrix will have exactly the same solution set. So this is what we need to show. We'll split the proof of our theorem into two steps. So the first step is the following lemma. Suppose x1 equals c1, x2 equals c2, xn equals cn be a solution of a system of linear equations. And let the new system of linear equations that we denote with a prime be obtained from the original system of linear equations with a single elementary row operation. Then the solution that we had, x1 equals c1, xn equals cn, is a solution of a new system SLE prime. We have elementary row operations of three types. In the last type, type 3, we interchange two rows or two equations. So this is the easiest case, because here we just change the order of equations, and the set of equations doesn't change. So clearly, the solution of an old system is also going to be a solution of the new system. Let us consider the most interesting case, type 1 elementary row operation. Proof for type 1 elementary row operation. Rs prime is equal to Rs plus D times Rp. Now, here I made a bad choice of notations because I use C's for my solution. Let's change this notation and call this constant a D. Let us compare equations in the original system of linear equations with the new system. So if I is different from S, then equation number I in the new system is the same as equation number I in the old one. So the only difference will be in equation S. So this means that in this case, these equations are satisfied because the given solution satisfies all equations of the old system. So immediately it will satisfy all equations of the new system except possibly equation number S. Now, let us look in detail at equation number S in the new system. It's made out of equation number S in the old system and equation number P in the old system. Now let us write down these two equations. What is equation number S in the old system? So this is written like this: AS1 x1 plus AS2 x2 plus ASN xn is equal to BS. what is equation number p in the old system. So that's AP1 x1 plus AP2 x2 plus APN xn and is equal to BP. Now, the equation number S in the new system is obtained by adding to equation number S in the old system d times equation number P in the old system. So this means that equation number S in the new system will look like this. So it will be AS1 plus D AP1 x1 plus ... plus ASN plus D APN xn and is equal to BS plus D BP. We need to show that if our solution satisfies all equations of the old system, then it will also satisfy all equations in the new system. For equations different from equations S, we already know this. So all we need to do is we need to verify that our solution of the old system satisfies equation number S of the new system. So we do this by making a substitution. We take a new equation number S and plug in our solution in this equation. And we need to verify that this equation will hold. Now we substitute. So for x1 we substitute c1, for x2 we substitute c2, and so on. For xn we substitute cn. So we get as1 plus dap1 times c1 plus ... plus asn plus dapn times cn. So this equals. So this can be split into two parts. So this is as1 c1 plus as2 c2 plus asn cn plus, now parts with d. So this will be d times ap1 c1 plus ap2 c2 plus apn cn. But we know that our constant c satisfy equations of the old system of linear equations. In particular, they satisfy equations number S and equation number P. But what we have here is precisely the left-hand side of equation number S evaluated at C1, C2, Cn. So this means that the first expression simplifies simply to Bs. So likewise, this expression is the result of substitution of our solution in the left-hand side of equation number P. So this is equal to D times BP. And that's exactly the right-hand side of the new equation number S. So the conclusion here is that x1 equals c1 ... xn equals cn is a solution of equation of a new equation number S. What we have just proved. So we proved that if we have a solution of an old system of linear equation and we apply one elementary row operation of type 1, then this solution will still be a solution of the new system of linear equations. And we also mentioned that type 3 case is completely trivial. So here we just change the order of equations. So of course, if something satisfied the old system, it will automatically satisfy the new system. And there is what's left is type 2 case, and I leave this case for you as an exercise. Now, we proved our lemma. We showed that if we apply one elementary row operation to a system of linear equations, then any solution of the old system is also a solution of the new system. Did we prove the theorem? So which said that these two systems have exactly the same sets of solutions? Not quite. Perhaps it could happen that the new system of linear equations has more solutions than the old one. So we only showed that every solution of the old system is a solution of the new system. Now, what we need to do is we need to do the opposite. We need to show that every solution of the new system is a solution of the old system of equations. If we show that, then we complete our proof, and we will show that these two systems have identical solution sets. Now, how can we prove that every solution of the new system is a solution of the old system? The trick that we're going to use for this is the second lemma, that elementary row operations are invertible. So this means that there is a second elementary row operation that will allow us to get the old system of linear equations from the new one. So if we prove this lemma, then we can just apply our first lemma to this situation in reverse. So by our first lemma, we will conclude that every solution of the new system is a solution of the old system, because the old system is obtained from the new system by one elementary row operation. So what are the inverses of elementary row operations? So for type 1, so if we add to row S d multiple of row P, how can we undo this elementary row operation? Well, what we can do is we can now take another new row S, where we take row S prime and subtract d times row P prime. Right. So here we claim that row S double prime is the same as row S. So indeed, what it is. So row S double prime is so row S prime, which is row S plus d row P. And what is row P prime? So row P did not change and on this step. So this means row P prime is the same as row P. So here we have d minus d times row P. And these two will cancel, and what we get is just row S. And all other rows are not changed here, so this means that they are the same. So what we see is that if we just switch the sign here, and instead of adding d multiple of row P, we subtract d multiple of row P, then this is again type 1 elementary row operation, and it will undo the given elementary row operation here. For type 2, So if we want to undo this transformation, then all we have to do is we have to divide by k, right? Or this is the same as multiplying by k inverse. And so clearly, so if we multiply a row by a non-zero constant k, and then multiply the same row by k inverse, then we will get the original matrix. And for type 3, the answer is also obvious. So here we just interchange two rows. So what we do is we interchange these two rows once again. And this will undo this type 3 elementary row operation. And so this proves this very simple lemma. And we show that old system of linear equations can be obtained from the new one by applying the inverse elementary row operation. And as a result, we complete the proof of the theorem, and now we conclude that the original system of linear equations and the one that's obtained by one or a sequence of elementary row operations, so this will have the same solution sets. Now, let us give a summary of our methods for solving systems of linear equations. So first, we write down an augmented matrix. For the system. Two, use Gaussian elimination algorithm to bring augmented matrix to row echelon form. Three, so check if there is a pivot in the right-hand side column. So if there is a pivot in the right-hand side column, the system is inconsistent and has no solutions. And we stop here. If 3 does not hold, then we apply further elementary row operations to bring the matrix to reduced row echelon form. So this part is called Gauss-Jordan elimination. So once we get reduced row echelon form, now we can extract solutions. So what we do is variables in pivot columns are leading. And all other variables are free. So here we identify and list the set of leading variables and the set of free variables. So we split our all variables into these two sets. So next we assign parameters to free variables. And express leading variables in terms of these parameters. Now, the number of parameters that we use is equal to the number of free variables. So it is possible that there might be no free variables at all. So there are cases, there are systems of linear equations where all variables are leading and there are no free variables. If this is the case, then there will be no free parameters. And in this case, we have a consistent system, but it will have a single solution. And so this solution will be expressed in terms of constants. There will be no parameters here. So once we have free variables, then we get a parametric system of solutions. In order to express leading variables in terms of the parameters, it is useful on the last step to take the matrix in reduced row echelon form and rewrite it again as a system of linear equations. From this system, it's easy to express leading variables in terms of free variables and thus in terms of the parameters. In this method, when we apply Gaussian elimination or Gauss-Jordan elimination, we use elementary row operations. And the theorem that we proved shows that when we apply elementary row operations, the set of solutions does not change. So this means that the solution that we obtain for the last simplified system of linear equations is precisely the solution set for our original system of equations.